Okay, good morning. Shall we start?
Hello? Can you hear me?
Okay.
Okay.
Yeah. So,
share my-
Zafira-san,
Hi.
you can start.
Can you see my screen, Sensei?
Yeah.
Okay. Last week, we tried to understand the relationship between degree of coupling and the relationship between the energy dissipation and the performance of the building. So we know that from the result here. So this is a different type of damper. So M is 20% metallic and viscoelastic 500. This is the optimum based on we find here. So we find the optimum energy dissipation. So the optimum energy dissipation at metallic 20% and viscoelastic 500%. And we try to see the performance when we combine these both damper together. So this is central, the first on the left and on the right is for Kobe. And this is
How did you get optimum?
based on the interstory drift and also here and the displacement based design. I have to check one by one, but the easiest way to see the difference is based on the interstory drift. So our limit is 1.28. So basically all the this damper is less than the limit that we target. And then after that we compare with displacement based design. So, but the first step because this is still initial study for displacement based design. So easiest way to compare and the fastest way just use time history analysis. And then this week, I try to compare with the different story height. So first of all, I try to, I forgot to tell you that last week we tried to see 2.5 meter wall because 2.5 meter wall is the weakest building. And we try to choose which damper is suitable to get the perfect performance for the building. And for 2.5, first we check for the viscoelastic from 200% to 1000%. Actually, we cannot achieve the limit because, and we also know that 2.5 meter wall is a small length of wall and the degree of coupling also a bit higher if we check here. So here you can see 2.5. This is 5 meter. This is 7.5. So if you can see 2.5, the degree of coupling is higher. And
which one is degree of coupling?
This one. Can you see this one?
Beta CB.
Yeah, beta CB degree of coupling. So degree of coupling higher means that the beam is stronger than the wall. That's why the percentage of beam is higher. And 5 meter is balanced between beam and the wall. And 7.5, we can see the wall is stronger than the beam because we can see that 7.5 length is longer than others. And then we try to check if we can improve the shorter wall length, which is 2.5 meter. And this is based on viscoelastic. So from this study, from this result, we can see that even higher viscoelastic metallic, we cannot, higher viscoelastic, we cannot achieve the target limit. And if we can see metallic damper also is exceeded the limit.
Yeah, if beam is stronger, I mean, because coupling ratio is higher, so you must reduce strength of coupling beam to make it weaker.
Yes, but we also
20% is maybe strong. You must reduce more.
Reduce more. But if we reduce more, Sensei, is the coupling, the damper will be damaged severely.
But I don't know. It's worth to check. And do you have a result of a displacement-based design of 2.5 meter?
2.5 meter. And it's here. So 2.5 meter. This is 5 meter. And this is this one. Yeah, this one's missing.
2.5 meter.
Yeah.
Uh-huh.
This
So
under central.
straight line is over than capacity curve.
Yes. And also under Kobe, this one
Mhm.
is
It's 7.5.
this one.
Okay, so it means your damper is, too strong, maybe. So you must find out capacity of damper so that this blue straight line and the capacity curve match together.
Yes, sensei. But the thing is, what I understand in coupling beams that the degree of coupling is very important. Like
Mhm.
like for example, like different height of story have different range of degree of coupling. So
Mhm.
basically 10-story building, the range is between 40% and 50% around that. So these two how can I say, like the first evaluation for the building is degree of coupling. So 5 meter and 7.5 meter, the degree of coupling is suitable with the design recommendations. But if you can say 2.5, the recommendation for degree of coupling is already out of recommendation. So it doesn't matter how we improve the damping, it's very difficult to achieve the limits. That's what I understand. Because I also try like 2.5 meter here, like 2.5 meter walls with different type of damper, even metallic damper with the lowest one, 20%. Even if I reduce to 10%, I don't think it will change much because the ductility, that it will damage the damper itself.
But you designed the damper by using displacement-based design,
Yes, yes, but
not coupling ratio.
yes, sensei, but because I don't have much time to do displacement based design one by one first, I try to see the performance based on time history analysis first, and then from that we can compare with a base displacement based design.
Yeah, but I think why the reason not so big difference these lines because response is almost elastic range. So if you 20%, 40%, 60%, if you change capacity of damper, but the response is even smaller.
Okay.
So I think 10% or even 5% may work to dissipate energy. So actually, this damper doesn't dissipate any energy.
Okay, I can try lower than 20%.
Yeah. But don't do time history analysis. You must check first by displacement-based design without doing any time history analysis. Because this is a design procedure we propose.
Yes, I understand.
No.
Yeah, I just use some history analysis first because it's faster, and actually displacement-based design takes longer
Yeah,
step.
it's faster, but it depends on the earthquake.
Yes.
But displacement-based design, you use design spectrum, right?
Yes, sensei.
So, how to say, you can get unique answer if you use displacement-based design.
Okay.
Mm.
Okay, next time I will just
Yeah.
use displacement-based design. And I also try to increase the the height of the building.
Mhm.
So 5
Of the
meter
building.
height of the building. So say how can I say, when the building is get higher.
Okay. 10-story, 15-story, 20-story.
Oh yes.
Okay.
Yeah. So we can the length the thickness of the wall I maintain as 500 mm.
Yeah, but also you must design based on displacement-based design.
Yes.
Yeah.
I just want to compare the performance. Then I will do the displacement-based design also.
How about the coupling ratio if you increase number of story?
I think it will change since I don't have sufficient time to take or to calculate all the degree of coupling, but this is my first step to see the fastest way to see the performance of the building.
Uh-huh.
I just want to see what happened when the height increase. I know that when the height is increased, the degree coupling will change.
Mhm.
Because it's also written in the textbook. It say when the number of height,
Mhm.
number of building is increasing, and the degree of coupling also increasing.
Mhm.
And then that's why I just compared like 5-meter wall and then with 7.5-meter wall because I know 2.5 will over the limit. So if we can see if the number of height of the building increase, the limit also the inter-story drift is almost to the limit because the building is more flexible. But when we compare to Accenture, is okay, but when I compare to Kobe, it's over the limit for 5-meter wall. But for 7.5, is still considerable okay for under Kobe. This is under metallic temper. I compare with metallic temper and viscoelastic temper first to see how it performs. And this is a 5-meter wall under viscoelastic. It doesn't have much problem under El Centro, but when it comes to Kobe, it is over the limit, especially for 20-story building.
So why?
Why? I think Kobe have like a very spark wave in the middle of the wave. So in the story is more compared to El Centro.
Why story height is larger, the response is also
Because when the height of the building is higher, the building is more flexible to bend compared to the short story. And the time, how can I say, the natural period of the building also different. And that's why the inter-story drift also different compared to other story building.
But there is no theory behind. You just analyze and you show the result, that's only.
Yeah. Like, for example, this one, this is from this Pole books, Sesame RC design. It's also show that if the length of the wall is different and the story drift also different.
Of course, it's different, but we must explain the reason
The reason.
theoretically.
Maybe if I have time to arrange more properly data, then I can find the theory behind the result. And then I also try to compare with combination of the building. And this is 20% metallic and 500% viscoelastic with different length of the wall. We can see that 7.5 has the lowest story reduced compared to 0.5. And also same with 15-story and 20-story.
Yeah. So
Yeah.
why? Why this difference happens? You must explain the reason.
When we have different length of the wall, the degree of coupling also different. So when the degree coupling of the building change, the interstory also change because the stiffness of the building also change. Degree of coupling is related between the strength
But
of the.
how do you explain? I mean, Kobe and El Centro, maybe you can explain by response spectrum,
Mhm.
but how? The degree of coupling affect what?
The strength of the beam and the strength of the wall.
Yeah, but of course. So what is the theoretical reason, theoretical explanation?
It's related to the wave of the earthquake.
No, it's not the explanation.
Mhm.
So how earthquake affect characteristic of earthquake affect? You are talking about the duration, or you are talking about the frequency?
From my understanding, Kobe is a stronger earthquake compared to El Centro,
Of course, it's stronger.
and then that's why the interstory drift is bigger than compared to El
So
Centro.
without using time history analysis, can you explain this?
Based on
Can you
displacement,
predict this difference
based on
without doing time history?
from previous the one from Tokyo Sensei that he took the mean. Okay, he took the mean earthquake, not the compared the stronger and the lower. So.
Or can you propose some formula to estimate story drift without the time history analysis? If you say coupling ratio affect the result, maybe equation include coupling ratio.
Actually, in the displacement-based design, they already have interstory drift formula. So based on degree of the coupling, they can predict the interstory drift. This is based on the Tokyo University students. So he compared displacement-based design interstory drift and time history result based on the mean earthquake. So he found a few selected earthquake, and then he can like this. He find the mean, and then he can predict the blue line and the red line based on calculation-based displacement-based design. So in the displacement-based design, he also have the calculation to determine the interstory drift based on degree of coupling.
We propose any formula?
No, we doesn't propose any formula, but this is from the books actually, Sensei. So this is this displacement, design displacement profile from this formula. Yeah. It's in the poly books actually. His method is actually same from the poly book.
Well, we don't use this formula because we do pushover.
Yes. Yes. But the problem is with pushover, we cannot apply to the viscoelastic.
Yeah.
And his study, Sensei, is only for diagonal beam and conventional beam. It doesn't apply with damper.
Well, I know. But we do pushover even viscoelastic damper with pushover, neglecting viscoelastic damper, then we estimate velocity. I mean, from the pushover result, we multiply omega, right?
Yes.
And we can get the velocity. And we can calculate the equivalent damping of this viscoelastic damper. So this is a procedure of displacement-based design.
Yes.
So you should estimate displacement response by displacement-based design.
Yes.
This is a how to say better. I mean, なんていうのかな。
It's the procedure that we discussed.
And you should improve how to get better result by displacement-based design.
Okay.
So first, you should use displacement-based design and compare with time history analysis. And if there is a difference, you modify displacement-based design. This is a study.
Okay.
This is a research.
Sensei, can I have one question? So we can see that El Centro and Kobe, the difference is too large, right, Sensei? Can we use mean, not like, can we compare the displacement-based design method with the time history, but not only to earthquake, but the mean earthquake? So it's more valid because if we compare to small earthquake and big earthquake, maybe the result in between is maybe good for a central, but it's not matched with the Kobe. So if we
So
can
you use El Centro, original El Centro?
Yes.
I mean,
No, we changed to artificial. We already changed artificial El Centro and artificial Kobe.
So both have the same response spectrum. Is that correct?
I use this one. This is for El Centro, and this is Kobe.
So they are made by stellar wave.
Yes, stellar wave.
Could you draw response spectrum of these two earthquakes? Well, yeah.
Okay.
By using view wave.
View wave.
You know view wave.
Yes.
Well, maybe next time.
This one, like this.
Yeah.
Okay, the number is 1.
And how about the time interval? 100 hertz, I mean 0.01 second time interval. No, it's 0.02. So it must be 50. Yeah.
50.
No, 50.
Okay.
And number of spiral header line is 2.
This one, 2.
Yeah, 2. Because the first is the number of data.
Okay.
Second is the time interval.
Okay.
And okay, that's okay. And could you check response spectrum?
Response spectrum.
Yeah, this one. Velocity. Acceleration is okay.
Acceleration.
Okay. Could you change axis to be not long? This is long normal. So could you change to be? I think it is なんだっけな。first period. Period. Could you do
this one?
No, なんだっけ。
This one.
Yeah, this one. Yeah.
Mm.
Select the period
Period.
and select scale in log normal at the top. Please, yeah.
This one.
No, second one.
Second
It's
one.
checked, but please release. Yeah. Okay.
Okay.
And yeah. And also, could you click again, same window?
This one.
And acceleration. One, two,
Acceleration.
yeah. And which one is log normal? No. Could you go down? There is a response spectrum, maybe. Acceleration response spectrum. Yeah. SA.
Okay.
No. Yeah.
This one.
Yeah. And
Okay. And
yeah.
then this
Yeah.
one.
Okay.
Okay.
And 3, 4, 5. Okay. Could you change the horizontal axis to be from 0 to 5? Period.
Period.
And 0 to 5.
0 to 5. This one.
This one is okay. And then second one, next one, the maximum is 5.
5.
Yeah.
Okay.
Okay. So this is a spectrum of El Centro.
Mm-hmm.
Please save this figure.
Save.
I don't know.
I can put here.
No, it's acceleration data. Could you cancel?
Oh, I
Maybe
screenshot.
I'm gonna get, please save the picture.
Okay.
Yeah, okay.
Save. Okay.
And
And,
please do same thing for that.
55. I think this
number
is
of file header is 2. Yeah.
2.
Yeah.
And then you can check.
Okay. You can compare both. Okay. Good.
Okay.
Good.
Okay.
Okay. It looks to earthquake has the same target spectrum. Okay.
But
Mhm.
why when we run time history analysis and the result is different, Simpson?
Yeah, this is very important. Okay. So if we do displacement-based design, we design the building based on response spectrum.
Yes.
So, and the response spectrum of El Centro, artificial El Centro, and the response spectrum of artificial Kobe are the same here.
Yes.
So it means that the result of displacement-based design will be same.
Yes.
But if you conduct time history analysis, you have a different result.
Yes.
So this is one of research target. Why? Because the difference, the spectrum is same, but the wave shape is different, right?
Yes.
Wave shape is different. So, so we must think about how to improve displacement-based design to consider, how to say, wave shape. But anyway, could you first design your building by using this target spectrum?
Okay.
And each, 2.5 meter wall, 5 meter wall, 7 meter wall. And for the case of the metallic damper only, for the case of viscous damper only. And if you want to do, you can combine.
Okay.
And find out the matching point. So you must do some kind of a repetition to get the convergence. So target spectrum, target curve is capacity curve is the same. You can get capacity curve by pushover. But the estimation by displacement-based design, blue straight line, change, right?
Yes.
Depending on the capacity of damper. And you try to get the convergence point. So this is a design procedure. So you must do it first. Then after you get the convergence, you go to time history analysis. Okay. So you don't do that. You jump to time history analysis. So we cannot discuss the reason why. the difference.
Okay, sensei.
Mm. Mm.
I will continue this for the displacement data and
Yeah.
come back to you.
Yeah. Okay, Saraya-san, do you have anything you want to discuss?
Yes, Sensei. Can I share my screen?
Yeah.
Sensei, so today I wanted to discuss that last week we completed one manuscript
Yeah.
on the optimum design part.
Mm.
So initially my plan for the Suzuki Foundation Fellowship was to do these three objectives.
Mm.
One was to devise the hybrid vibration control system, for which we prepared the conference paper in Italy next year, where we defined the different configuration of the hybrid vibration control system. Next was to obtain the optimized and robust controllers for lifeline structures under multiple hazards. So that we have prepared the journal paper. So now I have given that to Professor Matsagar, and I'm waiting for his comments on that. And next was to propose some design guidelines for performance-based structural design with the hybrid control system. So I have started this right now, so I don't think it will be completed by 1 month, but I will keep working on this. And by the end of the year, I think we can get one journal paper out of that. So uh, so my aim in this work would be to get the fragility curves of the structure with hybrid control system. So as far as I have seen in the literature, fragility curves of structures with both base isolation and TMD are very rare. So it has not been worked on. So we can work on that. And this figure I have taken from the paper of Khalid San and Edison San. So so the basic idea is in fragility curve, I have followed the control group meetings then when they were developing this paper, and I know the main procedure of developing IDA, and then how from IDA we can get the fragility curves.
Uh-huh.
So that part I know how to do. Now next one problem which I think I will face in this work is uh, in this basically in fragility curves we have to increase the demand, we have to increase the peak ground acceleration or spectral acceleration and do many nonlinear time history analysis. However, when we design the our unbonded isolators, so in that design part, we have to select a design displacement first. Otherwise, we know that if the design displacement goes above the limited value, then there is no definition of the trilinear curve after this. So it is restricted to design displacement. So now if we, what I assume is, if we design some trilinear isolator, and then if we increase the earthquake demand, obviously the design displacement will be exceeded. So how will my trilinear curve cater to that? I don't think my developed model could cater to that. So that is one problem which I assume I will face in performance based design. So in these cases, do you have any idea on how to tackle these type of problem? Mhm.
Mm. Mm.
One idea which I was thinking is maybe we can assume the equivalent stiffness and damping and then develop the fragility curves. And since the idea of performance based earthquake engineering is we have some probability of the hazard, then we develop some probability of the then we developed some fragility curves from the nonlinear time history analysis. Then we develop the like damage analysis, like for this engineering demand parameter, what is our damage at different levels, and then finally we get the loss estimates so that we can design that what at which point we want our structure to be. So maybe if we could say assume the equivalent stiffness and damping, develop the fragility curves and everything, and then from final we can then decide that which equivalent stiffness we want, and then we can use that to design the final isolator model. But like initially it is difficult to use the trilinear model for the fragility analysis.
So it means you use equivalent damping and equivalent stiffness. So it means you want to use response spectrum instead of time history analysis.
No, Sensei, I want to like maybe use the time history analysis, but then like to define the trilinear curve or to define the force displacement behavior of the isolator. Like I don't know if I can use this model. Maybe instead of the trilinear model, I am thinking of using the equivalent linear model
For time history analysis.
for time history analysis. Yes. And essentially, there is one more problem then. Now, if we include the equivalent linear model, so now we only have one stiffness. So our idea of using two TMDs with one stiffness in the stiffer one and the second one this one. So now we cannot use two TMDs. Now we have to use one TMD with only one stiffness. So that is one more problem. So maybe I was thinking is if I have to use the equivalent model, then I can relate that how that two TMD can be like used as one with the equivalent stiffness. If I could find some logic on how to use that model, then maybe it will work. But like I don't know how to do this. I'm still thinking on that.
So suppose you have a design spectrum.
Yes.
Can you find out the optimum TMD and the optimum isolator based on design spectrum
From
doing time history analysis?
From design spectrum.
If it's only base isolation,
Yes, sensei.
you can use equivalent damping and equivalent stiffness.
Yes, sensei.
But if you have a TMD, well, so wind force will also somehow simplified. I mean, designer cannot do time history analysis.
Yes.
So it's better to have a simple procedure only using design spectrum or static wind force. So I think it's better than fragility analysis.
Okay.
For the fragility analysis, I don't know how to say. It also depends on the earthquake you select.
Yes, sensei.
IDA, incremental dynamic analysis, you must do many calculations under many sample earthquakes. But still there is uncertainty about the selection of earthquakes and And I don't know how to check the accuracy of the result or how to use it for design purpose.
Okay.
So I believe a simple design procedure based on design spectrum, yeah, it's more useful.
Yes, sensei. So yes, sensei.
So reduction of response by TMD, it can be also, I don't know, modeled like equivalent damping. I've never seen the paper discussing about this. Right.
Yes. Maybe since maybe I'll have to see some papers since I'm not.
But it's a linear, if the linear system, we know how TMD works, right?
Yes. For the frequencies response.
Yeah. We can apply this formula for combining equivalent damping and equivalent stiffness of the isolator layer.
Yes. And then we can find some like optimum design from them.
Yeah, and also you can compare with time history analysis to check the accuracy.
Yes.
Yeah. Logistic analysis, people cannot check the accuracy.
Yes. And we already got some optimum design, so we can also compare our optimum from this with that. Yes, sensei. That is possible. So maybe sensei, I'll work on that.
Yeah, please think about.
Yes.
So, by the way, is the problem solved about citing paper you have not published yet?
Yes, sensei. I checked with like most of the big journal their guidelines. So they have the like provision that you can cite unpublished work also or under review work also. So even like for the referencing styles like APA and MLA, those referencing styles, I checked their documents and they also have provisions for that. So I think we can cite unpublished work also.
I have one idea.
Yes, sensei.
Maybe you don't like it. MDPI.
Yes, sensei.
This is a very quick review.
Okay, sensei.
But it's expensive.
Yes, sensei.
However, you have a Suzuki Foundation budget.
Yes, sensei.
So if you successfully publish in October,
yes, sensei,
you can request the Suzuki Foundation to pay for the publishing.
Okay, sensei.
I believe MDPI can review 1 or 2 weeks.
Yes. Yes, sensei.
So you can somehow, same content of World Conference, but a little bit. World Conference is too short, right?
Yes, sensei.
There are many things you cannot put inside.
Yes,
you can enlarge the content and published by MDPI.
Okay.
And also, World Conference paper is not reviewed paper, so I think MDPI is better than World Conference paper.
Okay. So yes, sensei. Maybe I can like first expand the World Conference content, and then I can send it to you. Then we can decide that if it is possible to send to MDPI.
So we must be a little bit hurry.
Yes,
and also we must talk to Suzuki Foundation about the submission fee because
yes, sensei.
I don't know how much in Japanese yen, maybe 30万だから in US dollar, $2,000 US dollar, something like this.
Oh,
Mm,
very expensive.
very expensive.
Yes, sensei.
Yeah. And Suzuki Foundation, I don't know. Is there upper limit of your budget?
No, sensor, there is no upper limit to that research budget. But I'm not sure whether we can use for publishing in journal. Like it is, I have to check with them.
Mm.
Mhm.
So yeah, it's up to you. If you want to try, I can negotiate with Suzuki Foundation.
Oh, okay, sensei. So maybe sensei first I prepare the big manuscript, and then we can discuss like
Mm.
whether it is possible to publish.
Mm.
Yes.
Okay, that's all.
Yes, sensei. That's
So, shall we discuss next meeting? So tomorrow, Mr. Ahmed from Egypt, he will come to Toyohashi,
yes, sensei.
and I think he will arrive university around 1 o'clock afternoon.
Mm.
And could you stay in your room, room
105, sensei.
105?
Yes, sensei. I'll be.
Maybe I will knock you.
Yes,
Knock
sensei.
your room.
Yes.
Okay, and introduce Ahmed-san.
Yes, sensei.
Okay, good. Okay, so let's see. Can you see my calendar?
Yes,
Yes,
sensei.
sensei.
29 today, and tomorrow, the next week. How about Friday? 1 o'clock afternoon.
I'm okay, sensei.
Yes, sensei.
It's okay?
Yes, sensei.
Okay. See you.
はい、ありがとうございます。